my friend David Sand, who is visiting us from Texas Tech up in Lubbock. This is, he was supposed to give this talk, well not this talk, he was supposed to come give us a visit a year ago before being iced in, snowed in.
It snows like twice a year in Lubbock.
Okay. We got him out this time.
We got him to Cook's Branch, but he was delayed by a day.
Yeah, that's right, that happened then. Yeah, exactly.
Okay, so you know, yeah, like they always say, if you don't like the Texas weather, just give it a day. So fortunately this year we've got him back. We're talking about an entirely different subject, I gather, which is pretty good. Give you a little bit of his pedigree. David finished his PhD with Richard Ellis at Caltech before taking a Chandler Fellow at Arizona, which is where I overlapped with him. And then to do it to sort of a weird quantum state, we were both in Santa Barbara and Harvard, depending on where your wave function collapsed.
Yes.
Building actual spectrographs for Las Cumbres Observatory.
Yes.
Before starting his assistant faculty job at
Texas Tech.
Faculty job, his professorship at Texas Tech. All right, so he's
probably take it.
one of the first speakers we've had this semester where we didn't have to get a visa to come visit us in Texas. So without further ado, thank you, David.
Great. Very happy to be here. Seems like a great town. So today I'm going to talk about moving near-field cosmology beyond the local group. Okay? So what I have here, this figure did not come out very well. I'm sorry about this ringing, or whatever it is. What you see here is a red giant branch map. Individual stars, red giant branch stars, in the halo of Centaurus A, or the nearest elliptical galaxy to our own. So these pixels, this is not some kind of smooth surface brightness map. These are real RGB stars, a map of RGB stars over degrees of the sky. Couple things to notice. This is a dwarf galaxy around Cent A. The hole there just means that there's crowding effects. Okay, so we're not detecting all the stars. That's okay. We're not looking for things like this. We're looking for things like this. This is a new dwarf galaxy that we've seen, low surface brightness dwarf galaxy, individual red giant branch stars around Centaurus A, which is somewhere down here. Okay? This hot pixel here is not a hot pixel, that's another dwarf galaxy around Centaurus A that we've also discovered. Okay? And if you can see it, this string here and this thing, right, this is a classic kind of S-shaped pattern of a dwarf galaxy being disrupted by Centaurus A. Okay? Does everyone see that? And if we had darkness in here, you would see other features. There's a stream here that's going off our field of view. There's some junk up here. This is sort of the continuation of the jet of Centaurus A. I'm really sorry this figure didn't come out very well. And there are new star-forming regions very far out along the jet of Centaurus A that we're finding. This is part of a survey that I'll talk to you about today. Sort of along the same theme of finding dwarf galaxies, this is a new dwarf galaxy associated with a compact high-velocity H1 cloud that we found. We don't know the distance to it just yet. It's very similar to Leo P, okay? And I'll tell you about our search for objects like this, isolated dwarf galaxies in the local volume, okay? My collaborators down there. I have to do this slide. You know, Texas Tech has a new-ish astrophysics group now, okay? Dr. Macron and myself were hired about 2 years ago. He does high-energy astrophysics, compact objects, okay? Just this last fall, Alessandra Corsi came to our department. She studies supernova, GRBs, gravitational waves, okay? And she came with her husband, Dr. Owen, okay, from Penn State. He's more of a physicist. He does just like waveforms for LIGO, things like that. Okay. So here's an outline of my talk. What is near-field cosmology, if you haven't heard that term? Okay. This is taking what we know about structure formation in the universe and comparing it with what we see in the local group, in the local volume, which is what I'm going to talk about today. Comparing basically what we see in simulations with our actual observations of structure in the local universe. Near-field cosmology. Okay? I apologize to Louis. This introduction is probably going to be kind of boring for him, but hopefully it'll be okay for everyone else. So what's the cold dark matter picture of structure formation? What are the problems with this cold dark matter picture? Okay, we'll talk about things like the missing satellites problem briefly, and something called too big to fail, another fancy problem with the cold dark matter paradigm. Okay. And from there, I'm going to talk about some of my work on the extended structure of new Milky Way satellites that have been found in the last decade by SDSS. But from there, I'm really going to talk about a new survey we have, newish survey we have with Magellan and MegaCam, where we're looking for new dwarf galaxies, faint dwarf galaxies, not just in the local group now, but we're moving on to our next nearest neighbors, Centaurus A and GZ 253. Okay? And we want to look for dwarf galaxies or signposts of structure formation, not just around other nearby galaxies. We want to find them in isolation as well, so that we can kind of tease out how stars form in these smallest dark matter halos. Okay? So we'll also talk about finding isolated dwarf galaxies in the local volume. All right? I'll talk a little bit about the future. Okay, so we know about the CMB. It's very smooth. There's some density perturbations. To go from those density perturbations to the rich structure we see today, basically, theorists use simulations, numerical simulations, to figure out, if you go from the CMB to what we have today, you assume some kind of dark matter particle. Okay? Mostly people assume a cold dark matter particle, which just means it's non-relativistic. Don't ask me what the particle is. Okay?
What's the particle?
It's a supersymmetric neutralino that hasn't been found in. Sorry.
How cold is cold? How cold is cold?
What's that again?
How cold? Half the speed of light, or like 1/100
I would
of the
say
speed of light?
it has to be less than that.
Well, it depends on when. In the
Yeah,
early-
exactly. I told you he'd be bored. He knows this better than
In
me.
the early universe, it's like, you know, 10th or something like that.
Well, that's why we
Now it's
asked
like,
him
forget,
to
now
be
it's-
here.
Now the thing that confuses me is axions, but maybe forget about that. Yeah, okay. Okay, so the point is, cold dark matter matches large-scale structure very well. I'll show you in a second. Maybe there's some room for a warm dark matter candidate or a self-interacting dark matter candidate. Okay? So this is a slide I show. The cold dark matter paradigm is extremely successful in explaining the large-scale properties of the universe. Okay? These two pieces of pie are a redshift diagram taken from Sloan and from 2DF. And then down here is from a numerical CDM simulation. Okay? If you do the statistics of the clustering here versus here, they're basically identical. Okay? So a cold dark matter particle matches large-scale structure very well. And there are other triumphs of the dark CDM paradigm as well. Okay? It's only once you zoom in to an individual halo where the problems start happening. Okay? Where you don't quite match simulations with observations. That tells you that maybe there's messy astrophysics going on. Okay? Or maybe we don't know our dark matter candidate well. Okay? So for instance, if you look at a cold dark matter halo, this is supposed to be something like the local group. This is from the Elvis simulations from the Irvine group, UC Irvine group. This is something like the local group. This is something like the local group. There are two big galaxies, Milky Way, M31. But then holy crap, look at all this other stuff. There are hundreds of subhalos. This is just dark matter, I believe. Okay? You look at this, there are hundreds of subhalos. Does anyone know how many satellites we know about around the Milky Way? It's like 20, 25. Same for M31. So maybe there are 50 that we observe, but here there are clearly hundreds. Okay? It's this mismatch that we call the missing satellites problem. Okay? It was first sort of brought up 15 years ago. Here's a nice plot. This is the cumulative number of subhalos around a given halo. All right, normalized by some global dark matter halo property, velocity. Okay, and this is what you get from simulations. These lines, the cumulative number of subhalos. And if you match that up with, say, the Virgo cluster, these dots here, the Virgo cluster galaxies. Okay, it matches the simulations relatively well.
But on a much bigger scale.
On a bigger scale. Well, this is supposed to be relatively scale-free. Okay.
Very cool.
And then if you go to the Milky Way, it's a disaster, okay? There are 2 orders of magnitude, maybe 1.5 orders of magnitude difference between the number of halo dwarf galaxies we see around the Milky Way and the number we would expect naively from a cold dark matter simulation, okay? That's just setting up the problem, okay? And of course, I'm not going to get into this, you can erase substructure by turning up the heat of your dark matter candidate, or turning up the speed, okay? Because it washes out small scale structure. All right, so a CDM halo may have this many satellites, but something warm has zilch, okay? All right, so that's one way to solve this. But it turns out it's relatively easy to get rid of dwarf galaxies, or it's relatively easy to have a dark matter subhalo never form stars. That's how I should say it. Okay? You could get ultraviolet heating from reionization. Okay? Heats up the gas, never form stars. Okay? Supernova feedback. Maybe you form a first generation of stars. Supernova goes off, blows out the rest of the gas. It never forms any more stars. And so you have some very faint dwarf galaxy, if you want to call it that, that hasn't been detected by surveys. Okay? Maybe there's tidal ram pressure stripping of gas, of dark matter subhalos around the Milky Way, and they never retain this, they don't retain this gas, and so they never form a dwarf galaxy. So there are lots of ways of keeping a dark matter subhalo dark forever. Okay? And one great result that sort of shows that we're hitting the floor of where stars form in dark matter halos came 6 or 7 years ago from Louis, where he showed, this is the luminosity of the dwarf galaxy, over 5 orders of magnitude in luminosity, all right? They all have roughly the same mass within 300 parsecs. Okay, this is telling us that stars, the magnitude between the number of stars in a dark matter halo, the magnitude between the number of stars and dark matter halo mass is stochastic, perhaps, at these low masses, okay? So you can have a 10 to the 7th solar mass dark matter halo that only forms a few hundred stars, or it could form 10,000 stars, okay? Very large range, okay? Now, I don't know the status of this, but I think this roughly holds true still today. Of course it does. Of course it does.
But by the way, Mark Aronson back in the 1980s saw this first in the classical dwarfs. This is much better data. Which is
Yeah, exactly. It does
But
definitely.
he was very puzzled by that.
It makes sense much lower.
Yeah, well, that's why you said, yeah, this is just much more convincing that there's a constant mass at lower end of the mass.
So a dwarf galaxy is only like 300 parsecs in size?
Well,
This is the core of it.
this is out to where you can actually, you have stellar tracers, am I right?
Yeah. So that's basically, I guess, like, sort of a central mass density, if you will. You know, right? It's not a proxy for like the total halo mass, at least for the large ones. So the Aronson results actually he used proxies to get the total halo mass. That's not exactly what this is. But
Yeah, I'm sorry if I didn't quite
no,
say
you
that.
actually did a very good job on
Well, thank you. Tell everyone.
Excellent.
Okay, I'll actually skip this one. Just suffice to say there are other problems with the CDM model of structure formation once you zoom in on small scales. And then the most recent problem, it's actually only a few years old as far as I know, is so-called too big to fail, which is sort of a problem named after the time it was found. So if you take the 10 most massive subhalos in a CDM simulation, where we think we know what's going on, and you compare them with the 10 most massive dwarf galaxies around the Milky Way, they have very different densities. Okay, this is sort of a proxy for the density or mass. Okay, but it's hard to measure. Okay, so the fact is, you know, the dwarf galaxies we see around the Milky Way are not as dense as one would expect if you looked at a CDM simulation. And it's in a regime where we think we understand what's going on, the most massive subhalos. Okay? So this actually is, I think, the bigger problem for now. Although it is relatively sensitive to the mass of the Milky Way. And we actually, I don't believe we know the mass of the Milky Way that well, to within a factor of a few. And that could change sort of the nature of this problem, this too big to fail problem. All right, meanwhile, with all this going on, I'm sure we all know that SDSS has discovered roughly 20 new Milky Way satellites in the last 10 years. Okay? Here's just a fun map of them. You use a match filter technique on color magnitude diagrams, and you just pick out stars that are consistent with an RGB, basically, at a given distance. And you can look for clustering on the sky. I'll kind of show you that here in a second. But we know, just from looking at SDSS, that there are probably a lot more satellites out there. Okay? First of all, this is an outdated plot, but you get the idea. SDSS has really only covered the northern sky. Okay? There hasn't been a southern survey yet for new faint satellites. And SDSS, as great as it is, only goes so deep. It only goes to 22nd magnitude. Okay, so there are probably small halos at large distances that we're missing. Okay? And so people have done some extrapolations and calculations to figure out that, oh, maybe there are hundreds of satellites around the Milky Way. Okay? And we're just not able to detect them yet. Okay? This greatly alleviates the missing satellites problem. Okay? So now, this is a set of slides that I've stolen from Beth Willman, with her permission, where I'm going to run you through some of the dwarf galaxies of the Milky Way. You tell me when you can't detect them anymore with your eye. So this is the LMC, 1/10 the Milky Way luminosity. That's pretty easy. NGC 205, this is a satellite of M31. Super easy. 1/40th the Milky Way's luminosity. 1/300th a Milky Way. This is Sextans B, kind of a dwarf irregular. I forget how far away. Leo 1, about 1/3000th the luminosity of the Milky Way. Still, something easily you can detect with your eye or with photographic plates. Leo 2, about 1/10,000th, very easy. Okay. Draco. I could still see this if I look from the back of the room and we turned out the lights. You could see a stellar overdensity here. So this is an MV of -8, absolute magnitude -8. Okay? And it's important to remember Draco because I'm going to tell you I can find Dracos like this around Cen A and NGC 253. Okay? And then there's this. 1/1,000,000th the Milky Way luminosity. Don't even bother turning out the light because there's no way you can find anything here.
Could be.
The whole joke is that you can't, there's no way you can find the dwarf galaxy.
Now you can show us Draco.
Yes, I will do that.
I actually could find Draco, so you see better than me.
Come on, look at it. Well, it's supposed to be pretty hard. Draco is actually right at the dividing line of the new ultrafaints and the classical dwarfs varieties. NV -8, 8.5. Okay. All right, so how do you find the dwarf galaxy there? Well, we know an old stellar population has a red giant branch, maybe a main sequence turnoff, depending on how far away it is. This whole thing goes up and down depending on the distance. Okay? If you pick a distance and you only pick out stars consistent with a red giant branch at that distance, make a map of it, maybe smooth it, do some cheating, and you get something like that. Okay? This is your new dwarf galaxy, Ursa Major 1. That looks like a piece of junk, at least to me. Okay? That's not a normal sort of spheroidal shaped thing. Okay? Nonetheless, people have gone out, measured velocities of stars in there, and measured some kind of mass, and it fits on that relation. Okay? The question is something like this, is this really a self-bound dwarf galaxy, or is it being stripped by the galaxy? By the Milky Way, sorry. So I've been trying to look at it from the other end, from the observational end. You know, comparing what you see in a CDM simulation with what we observe is a very hard thing to do. Okay? Connecting observations with simulations is not trivial. On my end, I have to have deep observational understanding of these objects to try to fit them in context with what CDM is trying to tell us. Okay? My key questions are these things all dark matter dominated? Are these things being stripped? Are they just stellar remnants of larger objects, tidal streams? how do stars form in these smallest dark matter halos? Okay? What's their orbital history, etc. Okay? So here's the place of these new dwarfs. This is half-light radius, log half-light radius, versus absolute magnitude. You can think of them as an extension of the old classical dwarf spheroidals, right? Sometimes they're not any smaller, okay, but they're certainly fainter, sometimes smaller, okay? And to put them in context, here are the Milky Way's globular clusters, okay? So an object like this, well, what the heck is that? I don't know. Is it a globular cluster or is it a dwarf galaxy? And then there are other very tiny things that are thought to be very small globular clusters that have been discovered. All right, so when I look at maps like this, RGB map, red giant branch maps like this, I think these things are the result of some kind of car crash or being okay? They're very elongated, amorphous morphology. Right? This is over roughly a degree on the sky. Okay? So the question is, can we get some kind of definitive proof that these things are not sort of self-bound dark matter halos, but they're really something being ripped up by the galaxy? So quite a while ago now, actually, I used the LBT. Ever heard of the LBT? And its camera. You think the LBT doesn't work now? It definitely didn't work back then. Okay? And nonetheless, so here are the fields I got around this dwarf galaxy. It was known, it was discovered at the time. It was known to be elongated. And the idea was to sort of tile along this sort of extension of the semi-major axis. Okay? That didn't quite work due to various problems with the telescope pointing. But nonetheless, we got a very large mosaic of Hercules. Okay? If you pick out the red giant branch stars, you get a map something like this. Okay? Very elongated. There's a little bit of smoothing here, so it makes it rounder than it actually is. Okay? Very elongated. Some signs of a stream. You kind of have to keep in mind that there's some gap here, right? So maybe that continues over here, maybe it doesn't. I've tried to guide your eye with this dotted line. So to me, I mean, the answer is maybe. I don't know. Is this something being
Is that a luminosity control or a cloud?
So it's basically you take all stars consistent with the isochrone, all the RGB stars, and basically count them in pixels, so like 10 arcseconds or something. Okay, so it's kind of proportional luminosity, but convolved with this isochrone. Okay, and then, of course, just to confuse you, I've taken all the blue horizontal branch stars, which have relatively little contamination. I've made them red on here, and I've plotted where they are, okay? And there are lots of blue horizontal branch candidates well outside the main body.
Because they're at the distance of.
At the distance,
Right.
exactly. They're at the right distance. Okay, so maybe. And I've tried to plot some color magnitude diagrams at the position of some of these nuggets. Basically, I don't know. Maybe, maybe not. Okay? Right, I'm not trying to sell you on anything. It is suggested. And we've done this for a large fraction of the new Milky Way satellites now. We've gone out and gotten deep imaging, made these RGB maps effectively of these objects. Here, the blue dots are actually blue horizontal branch stars. Well outside the main body, okay? And maybe there are some signs, I'm going to guide your eye again, some signs of tidal strip. Or maybe not. Yeah, exactly, you don't have to buff it. And here, the arrow is pointed towards the galactic center. Okay? I didn't make that up either. So I think the answer there is maybe. Maybe a lot of these new Milky Way satellites are actually being actively stripped by the Milky Way potential. You can't definitively tell that from what we have so far. So what we're going to do is we're going to get Keck follow-up, DMOS follow-up, and get spectroscopic velocities for all the RGB star candidates. within these mask regions. This is the DMOS mask form factor, okay? And in fact, it's being calculated that Hercules, if it's really being ripped up, it should have a measurable velocity gradient across this of like 10 kilometers per second. Okay? So that's coming up in May, where we'll sort of definitively decide or figure out if some of these objects are actually being actively stripped. In that sense, they wouldn't be, once you see star stripping, it means the bigger dark matter halo is wrecked at that point.
The devil's advocate, can you infer that it's actually being tidally broken up as opposed to just rotating? I mean, we have enough resolution to do that.
Yeah, exactly. Well, maybe not. This thing at the time, it has an ellipticity of about 0.7. So there are no spheroids besides these things that have an ellipticity that high. It's sort of marginal, okay? So maybe people have suggested maybe these are rotating objects.
My
Exactly.
opinion is like that, if that's completely, those two effects are completely degenerate, and given the small sizes of stars that exist that you're getting data for, I think that's pretty systematic. I think so it's something we can
It is
it is a systematic, yeah.
So
I mean, if you want to do this, put like a
We're really
rotation
sampling,
along. Yeah.
There are only so many stars we can get per minute.
Yeah, exactly. Yeah. No, it's true. Some of the big ones are absolutely not rotating, right?
Yeah, that's right.
So I mean, maybe that's the same assumption here.
The Boston dispersion there.
The dispersions are like,
Whatever master for.
yeah, well, the dispersions are much larger than basically. Well, the upper limits on the rotation are, were like a kilometer per second compared to the dispersions of like 10, at least for some of the big. I think there's one anchor on the satellite that's rotating. Anyway.
That's upcoming. I'll write the paper anyways, even if it's ambiguous.
As you should.
All right, so this has not only been done around the Milky Way, but it's been done around our neighbor M31. Right? There's the PANDA survey. Crap, don't ask me to remember the acronym. Pan Andromeda something something. Okay? Basically, they surveyed out to 150 kiloparsecs in radius, 3 magnitudes below the tip of the red giant branch. Okay? Look at this gorgeous map. There are all signs of structure formation here. We have streams. Look at this, connecting M33 with M31. Okay? Here it's better outlined there. And they found of order, 20 new dwarf satellites around M31. Okay? Really, really fun stuff. With a big allocation of CFHT time. Here's just a color version of that map. I think the colors correspond to metallicities here. So you could actually, sort of back out what the metallicity of the progenitor dwarf was that's getting ripped up here. And if you compare the M31 satellites with the Milky Way satellites, they're roughly the same, right? They have roughly the same properties in terms of luminosity and half-light radius or metallicity. Okay, actually you can measure them via spectroscopy for the M31 satellites. Okay, so the red and blue dots here are M31 satellites, and the little triangles are Milky Way. The point is they're hard to distinguish from each other. Obviously the error bars are bigger for M31 because they're farther away. So one thing I have to say is that there have been no simulations or completeness calculations yet for the M31 sample. Okay, so where do we go from here? The local group has been done very well, okay? But there should be some worry that our baryonic solutions to these problems are maybe tuned to the local group, okay? We want some statistics, right? We want to go from 1 to 3. So this is, understanding galaxy formation by just looking at 2 spiral galaxies in a loose group. Well, you can't quite do it, right? We got to go out and look at new environments. Heck, let's look at an elliptical galaxy and figure out what its satellite luminosity function is. Okay? So the next step, I would argue, is to go out to our next nearest neighbors, okay? And to even look for isolated systems outside in the local volumes. Little dwarf galaxies that haven't interacted with anything during the universe, during the age of the universe and figure out what their star formation history and properties are. Okay? So these are the two tracks that I'm trying to move on. So two of our next nearest neighbors, of course, there's M81, but there's also NGC 5128, which is Centaurus A. Okay? And there's NGC 253. 253 is kind of a Milky Way analog. It's roughly the same. Yeah, exactly. It's roughly the same mass. We think it's Milky Way, kind of a starburst galaxy in a filamentary environment, okay, in the Sculptor group. 5128, well, you can kind of just tell by looking at it that it's kind of a train wreck too. It has a big dust flame. There's clearly an AGN jet there. Okay, you can even see shells, all right, from some past merger. Okay.
Can I see?
Yeah.
NGC 300 too small to be bothered with?
No, I don't think so. I think it's important to go down to smaller galaxies and to do the same thing. And I'll talk about that a little bit at the end. Okay, and then the fun thing for this is that the last survey for satellites around these two galaxies was done with photographic plates. Okay? And so they were only complete down to a -14, absolute magnitude of -14 or so. Okay? So this is what we're going to do.
By the way, I took some of those plates.
I'm sure.
That's how old that's how long ago it was. So.
Okay, so here we go. We have to have an acronym. We flip the coin for this. The Panoramic Imaging Survey of Centaurus and Sculptor, Pisces. The other acronym was going to be DANG, Dwarfs Around Nearby Galaxies, which was my vote. But
Yeah, that was the winner.
talk to my postdoc. All right, so our weapon of choice is Megacam on Magellan. It has a 24 by 24 arc minute field of view. You know, the beauty of Magellan is that you could get 0.6 arc second seeing, and at that point you really kill it. Okay, you could go down to 26 magnitude very quickly. And so just to put it in perspective, here's M31 and the PANDA survey, and here's what we're going to do around NGC 253. This is just a DSS image. There's 1 degree. There's the Megacam field of view. That's a lot of field of views. I think it's 130 fields of view. Fill this up. And these little things here, little diamonds, blue diamonds, are the new dwarf galaxies we've already found. Okay? So, and remember, this is all in resolved stars. We go down to about 2 magnitudes below the tip of the red giant range. Okay? That lets us measure distances, roughly, rough metallicities, etc. Okay? And in the end, the idea is to compare this to the local group and, of course, simulations. Okay? There has to be some scatter halo to halo in the dwarf luminosity function at the super low end. Okay, so many new dwarfs, it's very easy to find them. They just pop right out, right? Because they're small on the sky, they're 30 arc seconds, roughly. And we can resolve out individual stars, but you also expect some low surface brightness material of the stars you can't resolve there as well. So I think do you kind of buy that? And actually, you can almost see this in a DSS image. I think it wasn't found before because of this bright star nearby. Or wasn't sort of mentioned before. And so you could fit some isochrones. Here's some AGB isochrones. This red giant branch, okay? Now, if you take stars in this little box, sort of an AGB star, and these are RGB stars, and you plot them here, if you could see the red and blue. So the AGB stars cluster around this dwarf, and so do the RGB stars. That's clear detection. And remember, this is 65 kiloparsecs away in projection from NGC 253, but there still are some halo stars around, maybe. And that's absolute magnitude of -10. Okay? That's 4 magnitudes fainter than sort of these photographic plate surveys we're able to get down. Sometimes you can't see these dwarf galaxies. Okay? So I'm drawing, this is an RGB map of that field. They're supposed to match each other exactly. Sorry, that didn't quite work. But here, if you look at the image, if you stare at the actual image, it's very hard to actually see that there's something there, but there's clearly some kind of elongated, maybe satellite, maybe the beginning of the string here. Right, does everyone see this over density? And so they all don't just pop out at you. Okay, and here's a little simulation I did, sort of the beginning of the big simulations we need to do to get understand our completeness in this survey. I've put in a fake Draco into our data. So an MV of -8, 8.5 or so. On the left, there's nothing, you can see that I implanted it right here. These are the few RGB stars we could actually detect. With the dwarf detection algorithm we're using, even that just a little clump, right? All the stars that close together that are consistent with the red giant branch just pop out very easily in our maps. Okay? Of course, I've shown you the best version of that. But at least we're going to have some machinery to understand how well we're doing, some completeness. Okay?
Doesn't make sigma detection, how big would you say you go? Is 3 sigma good enough for 5?
The problem is you have to, no one's going to believe that. So you have to go follow it up. Well, maybe some people believe it, but maybe I don't. And so you have to go out and maybe get HST follow-up or something. If you're ever on the
You
test.
enter 8 sigma points.
Yeah, the
Yeah.
problem is you do some smoothing and things like that. So 8 sigma is like not quite 8 sigma, actually.
8 sigma smoothed by some kernel.
Exactly, yeah.
You want HST because you want to resolve the individual stars even better.
Yeah, we want more stars. We want to know the distance very well via tip of the red giant branch. We want to be able to measure metallicity. You want to measure the size, okay, in order to compare it directly with the local group for the sample.
You need the resolution also.
Yeah, and depth. If we go 2 more magnitudes down, it helps. Okay, and so that's your Draco there. Draco, just at different distances. And I should mention that my postdoc is doing a lot of the heavy lifting here. I'm sorry, I should have mentioned this earlier. Denia Sinojevic, okay? And so here's her first big result. A close pair of satellites around Cen. Showed you that in the title slide, okay? This is a very low surface brightness galaxy. Maybe you could kind of pick it out there from the actual DS9 image. Okay? And there's clearly something there as well. And it just pops right out of our RGB filter. Okay? So this is an RGB map. For some reason, that one came out better. All right. So this is 90 kiloparsecs away from the center of Cen. Okay? And they're 3 kiloparsecs apart. And this is just a tease. Maybe this is a satellite of a satellite, something else that is predicted from the cold dark matter sort of picture structure formation. Okay? So it's very hard to confirm. Here's some color magnitude diagrams. Here's of this big object over there, very clear, versus a field color magnitude diagram. I mean, we're really getting hundreds of stars associated with this dwarf, which you cannot see at all in the DSS. Right? It's too low surface brightness. And here's the smaller object. It's harder to see. These are same area CMDs, okay? But there's clearly something there, okay? And here's how they fit in so far. This is the first sculptor dwarf I showed you in red versus this pair of dwarfs. And I plotted, I think, the Milky Way and M31 satellites on here, their size versus their absolute magnitude. Okay, they fit right in, kind of boring. Absolute magnitude versus central surface brightness. We seem to be hitting an edge here, sort of the edge of where things have been found in the local group. All these dwarfs, even in the local group, have some completeness limits, and we think we're missing some low surface brightness objects. Okay? I'll keep zooming, I'm running out of time. All right, and so this is sort of the map that we have so far today. We have more data. It's a lot of work. Okay? This is a known dwarf. We blow it out in the center. Okay? Because we're trying to get much deeper. And we're really seeing some interesting structure. This is a dwarf that's being dismembered by Cen. You see signs of other streams here. And these things persist over several megacam pointings. We really believe that they're there. Okay? And this in particular with this S-shaped pattern. It's really
Have I been drinking too much, or do I see an arc at the end?
Yeah.
I worry, well, sometimes I think that it's even sort of associated with this, that there's a connection there.
And it's all in projection mode, so you don't really know.
Yeah, exactly. Actually, so that's a good point. We actually have like 20 hours of VLT time just to hammer basically here and here to see if we can measure some kind of velocity gradient along this string. It's sort of a pilot test program. Okay. Unfortunately, Sen A is too far south to hit with Keck or something like that. You really have to go to VLT. All right, there's the CMD of the little central dwarf there. Looks good. And here I talk about VLT VMOS. Now you guys should be thinking about GMT, of course, because GMT could totally handle this kind of stuff.
Part of the science piece.
Here I thought the Gmax, yeah, PI was good. So we have upcoming HST follow-up of our Sen-A satellites in particular. This is the object where we have our act more together, I guess you could say. And we are able to put in an HST proposal last round. And we're really going to follow up all our dwarf candidates. There are about 15 of them. Invite me back once that's done. Or invite my postdoc. Okay, so let me stop here. I'm almost out of time already. So let me pause. If you have questions here, I'm going to talk a little bit about faint isolated galaxies in the local volume. Okay, yeah?
Just had a question about Sen-A. I mean, do we know anything about the object that merged with it or that was engulfed by it, and would that matter? Is it a major merger that would have brought in a lot of dwarfs?
I know less than I should about that. I think people thought it was a tens of % size of Sen-A originally. And maybe there's, I don't know what the evidence is, but I think people think it was a spiral galaxy.
There's a lot of galaxies.
It's got a different life outside here. Yeah.
So, our eyes are very good at maybe seeing things that aren't necessarily there. Have you guys have any like machine learning kind of things where the computer is a little bit less biased?
Machine learning. If you have a good idea as to how to approach that, I would love to hear it. I mean, basically right now we're making red giant branch maps.
You can teach the computer to look for clustering, for example, in the maps or something.
Yeah, I would be happy to explore that kind of thing. It's a little bit out of my, happy to learn, sure. Are you on my schedule?
No.
Okay.
But, yeah.
Okay, so that's one end of things, okay? We know the satellites around the Milky Way and M31. We want to broaden our view of faint satellites by looking in new environments. We can do that now with new instrumentation on Magellan. LSST is going to kill this, okay? We're going to do this for all kinds of new, local volume galaxies. GMT is going to kill this, okay? Because then you could follow them up very deeply. You could even pretend to get kinematics of some of these objects, okay? The other end of this, so these are sort of roughly similar environments to the local group, but not quite. Let's go to sort of an isolated environment. How do we find dwarfs in isolated environments? Well, the thing that people are doing now is they're looking in H1 catalogs. H1, neutral hydrogen gas. There are two new surveys, Alfalfa and Galfa H1. They've done maps of 7,000 square degrees in the sky. You know, roughly 10 kilometer per second resolution, couple arc-minute beam. They can find 10 to the 5th solar masses of H1 out to a megaparsec. Okay, so if you imagine you have a blue star-forming galaxy out there, just beyond the local group, you can find it in H1 and then look at it in the optical and see if there's anything there. Or maybe there's just H1 and no stars. Wouldn't that be fun? Okay? Of course, you can never measure the distance. Okay? So there's this new-ish class of objects, ultra-compact high-velocity clouds. These are not your high-velocity clouds, they're ultra-compact high-velocity clouds. High velocity because they can't be sort of consistent with Milky Way gas, otherwise it's confusing. Ultra-compact so that they can maybe correspond to a dwarf galaxy in the sky. All right? And luckily, these two great surveys have published catalogs of these very compact things on the sky. All right? Velocity, LSR, greater than 90 kilometers per second. And the thing is, no one has actually gone out and looked, even in DSS, at the position of all these things to see if there's a dwarf galaxy there. So guess what? I did. Oops. And here's what we found. Out of those 80, I took whatever public data I could, SDSS, DSS, Galax, okay? Here's sort of their pointing error. And here are all the blue galaxies that are sitting at the position of these H1 clouds. Okay? Now, the reason why I got this idea is someone had already started doing this. They found this galaxy Leo P associated with one of these ultra-compact high-velocity clouds at about 2 megaparsecs away. Very gas-rich for the number of stars it has. MH1 over M star of about 3. And it's a very faint galaxy, about -8. That's about it's fainter than Draco, okay, out at 2 megaparsecs. Spectra of its H2 region shows it to be very metal poor. So maybe this is a galaxy, a pristine galaxy. We talked about high redshift galaxies today, that hasn't interacted with anything since the beginning of the universe. Still just forming new stars now. Very metal poor, okay? And now we have a sample of these galaxies. Some of them have been found by other people, but we've just finished up the first systematic search of these things. Okay? Oh, these are the other guys who've looked as well. We have spectra of all 5 of them. Okay? They all have H alpha at the same velocity as the H1 cloud. Done. That seals the deal. Okay? The plan is to go back and get H2 region physical measurements of these things with spectroscopy. The problem is we don't know the distances to these objects, okay? They're just little blue blobs in the sky. So we could guess, we could say, oh, they're at the Hubble flow distance. Or, hey, I resolved some stars. That means it has to be, maybe it's at this distance, okay? It's not very good. So I put bars down with our distance uncertainties, okay? So this is absolute magnitude versus half-light radius. All these bars are our new galaxies that we found. Couple things to notice. They sit with the other dwarf irregulars in the local volume. They're just dwarf irregulars, okay? That's right, here are some other gas-rich dwarfs in the local volume. This galaxy is this one, up here, which actually was only found in very deep CFHT data in our own Magellan Megacam data. If you look in SDSS, there's nothing there, okay? So it tells us we have some obvious surface brightness limit, okay? Because if you go deeper, you find more things. And in fact, if you do my search, you say, oh, all these galaxies were in SDSS, we look for things 10 arc seconds on a side, okay? And given their luminosity or their apparent magnitudes, you could come up with some rough surface brightness limit for our search. And it basically sits right where our objects are, okay? So we're clearly surface brightness limit. These are lines of constant surface brightness. By the way, all the dwarf searches are surface brightness limit. You know, they're all sitting on these lines of constant surface brightness at the edge here. Even the local volume dwarf irregulars are. So I would posit that there are tons of other things down here. There are other local volume dwarf irregulars to be found. Okay? We don't know a lot. And here's their H1 gas mass versus their stellar mass. Some of these objects are very interesting. They are dominated by H1 versus stellar mass, okay? This is almost 100 times more in H1 mass than in stellar mass. Okay? And a few objects like this are being found now in the literature. Okay? Very inefficient star formation. These objects are still turning their gas, which they're still dominated by, into stars. Okay, so where do we go from here? I'm close to out of time. Well, here's where we're going for now. The next step, you mentioned NGC 300, I think. We're actually going for NGC 3109, which is a biggish dwarf galaxy. We got DECCAM time next month to do a survey out to 75 kiloparsecs, which is roughly its virial radius. Right, this is 3 by 3 degrees. DECCAM is so awesome. Look at this, this is killer. So in 2 nights, we think we could do this, right? And find all the dwarfs down to an absolute magnitude of -6. Okay? The weird thing is we don't quite know what to expect based on CDM simulations. You know, NGC 3109, I don't know a lot about it, but I know now that it has a neighbor Antlia, which you can see in DSS plates, absolute magnitude of -10. You don't normally see that in CDM simulation. Dwarf galaxy with sort of a absolute magnitude -10 forth. Okay? And my postdoc went around and looked for other fluffy things, even just in this field of view, and there's all kinds of stuff. It's probably background junk, but it works for a proposal. These could be dwarf galaxies around, okay? Because look, Antly is just a big piece of fluff. Something else that I'm involved in is black gem. I'm really wrapping up now. Black gem, if you remember the beginning of my talk, we have 2 new faculty members who are very into LIGO. And we're very interested in electromagnetic follow-up of LIGO sources. One of the optical experiments that is looking for electromagnetic counterparts to gravitational wave events is black gem, okay? It's led by a group in the Netherlands, Paul Groot, okay? Ultimately, this will be 16 about half-meter telescopes, each with a 2.7 square degree field of view on the sky. I don't want to get off track, but gravitational wave events will have huge error circles on the sky because there are only 3 detectors on the ground. So they need to be able to survey huge areas of the sky very quickly, okay? And Texas Tech is trying to buy one of these telescopes. Well, we're already involved, but we're trying to fundraise for an extra telescope to be more involved. The idea is in the first year of operation, Black Gem will do a full sky, southern sky survey down in Chile. Okay? And from that southern sky survey going down in RF22, you could basically do a Milky Way search for dwarf galaxies, but in the south, which has not been done yet. Okay? SCSS did it in the north. Black Gem hopefully will do it in the south. Remember, SkyMapper was going to do something like this, but SkyMapper is not quite working out. DES will do about a quarter of this. So yes, they will find things and they will find them. We say that we're complimentary. Okay, so let me wrap up. We're trying to tackle this near-field cosmology problem, matching our expectations for galaxy formation with what we actually observe in the local group and local volume from a number of angles, okay? We're going after our next nearest neighbors, Sen A and NGC 253. We're looking for isolated dwarf galaxies as discovered by H1, compact H1 clouds, okay, to learn about their star formation. Hopefully we're going to do a survey of the southern hemisphere to find new dwarf galaxies there as well, in this unsearched space, complementary to DES, okay? And we're actually looking with DECCAM next month at sort of a lower mass halo, NGC 3109. I don't have enough time to get it all done, but whatever. Okay, thank you so much for having me. It's been a real pleasure. Hope to talk to most of you this afternoon.
You're right on time, so plenty of time for questions. Yes, sir.
Earlier when you show the, I think it's LBT images for those like a stream-like things, do you have any like proper motions for those things to look at the kinematics?
Well, people are going to do proper motions. I'm not really involved with that. I think there's a program now called HST Promo. I don't know if Hercules is a target for that. Maybe Louis does. I think
It might actually be on that proposal.
Yeah, exactly.
I actually forgot, but I don't think it is actually.
It's actually pretty far away. It's like 130 kiloparsecs
You
away.
can only, I think this requires like 10-year FX. And Hercules only did it for, well, Spectre only came out there.
Yeah.
The 6 years.
It's like when it's quasar.
Yeah, that's when it's, yeah. So I think that the main ones you can do with the proper motions, I think, right?
And another question I have is, I think you are all using the red giant branch stars to study these, so you presumably know the distance of all those candidates, so that you can know those are all the giants.
It's
To get rid
it's
of the
mostly
dwarf
the other way
population.
around, right? Like we're only looking for dwarfs at that distance.
Yeah. So I'm saying like all what I understand like you are doing like you know where is the distance of the dwarf the center, and then you're searching around to find it and assume
Yes.
the distance is the same.
Yeah, I mean, we tweak it a little bit within like 500 kiloparsecs, so, but it turns out with our ground-based data, it doesn't matter that much. That's about as good as we can measure the distance with the ground-based data, especially when they're so faint. Yeah?
There's one of your diagrams you showed with RGB and AGB stars. I was a little surprised at the number of AGB stars. That does not look like a very, very old population. It looks more like a Fornax or a population of a couple billion-year-old stars included in, you clearly have the tip of the giant branch, there's no doubt that you've identified this, but that's a heck of a lot of HEV stars in a whole population.
I agree.
That's really interesting.
Yeah, exactly. Yeah, exactly. I didn't mean to paper over it. We do talk about it in the paper, but yeah, that's right. There are intermediate, at least intermediate age, younger even stars in this. But there's only so much more you could say when you have a CMD like that. Yeah.
Also, there were blind searches not recently asked for objects that were just purely H1. Cameron collaborate did this. They looked in the off beams of the telescope, and they only found one, as far as I know. There was objects. And
Kidman.
so-
Okay, I'll have to look that up.
And the data, I think, was Chuck Woodward, maybe the other authors. They searched for objects that had absolutely no stars,
Yeah.
as far as they could tell. But
Exactly.
you're going much deeper. There could be stars in this one object, which was an H1 cloud with 85 stars.
I think that's worth looking into because there was, 10, 15 years ago, as far as I know, there was this idea that HVCs, high velocity clouds, could host stars, or that maybe they were the missing satellites. And I don't think I think that's worth revisiting.
That's not completely gone away. It's just.
Yeah, exactly.
It's kind of a backward.
Yeah.
How can you find H1 without the stars?
Well, first of all, computationally it's very difficult. You got to look back into the data, radio data, which has been reduced, but it takes a huge amount of computation to do that because they weren't looking for the H1 clouds; they were looking at another object. This thing just happened to be in the beam, and so it would
So the
take.
radio data is in a 21 centimeter. Oh, okay.
So now there are these two, I think they're actually, I don't know the details here. I think they're actually using, it's all Arecibo data, and I think they're using the same data, but just processing it differently, these two teams. And they've come out with different catalogs for these ultra-compact high-velocity clouds, which are these pseudo-dwarf candidates. But they put out 80 objects, and we only found 5 with dwarfs associated. So maybe a lot of these things, well, maybe they don't have stars. So worth following up deeper. I think it's going to be hard to get time for that, unless we have some really good candidates.
So the spectra,
Yeah, go ahead.
can you show the spectra?
I mean, it's just H alpha. I did it on purpose.
So do they have nitrogen or oxygen?
For this good spectra we have, they do have the full suite of H2 bonds. And we can do temperature stuff, metallicity stuff. But the idea is that, actually, it turns out, it's hard to know where the H2 regions are here. For instance, we put a spectra, the slit down here, and I only got a little bit of H alpha out on the edge here. So I almost feel like I need to go out and get H alpha imaging so I can figure out where the H2 regions are, and then get spectra. Which means it's like years away.
So these things are actually forming stars.
Yes.
I mean, say 1 or 2 ionizing.
Yes, certainly. And certainly this poster child, Leo P, has one H2 region
Correct.
right there. I'm here all day.
What is extremely metal poor?
We can look up the paper after. I forget off the top of my head. Yeah. Yeah, maybe if you know.
I think 7.12.
Okay.
We're arguing correct.
Yes.
So use an observer, so like, how many, you said you want to solve this statistically, right? This is how you address the satellites it's using.
Well,
Which
it's
I think is great, I think that's like actually.
It's half a lie, right? Because I could go from one
No, no,
local group to 3 or
No,
something.
but okay, what is like, in terms of these types of observations we've been talking about, like what's, from an observational perspective, what's a reasonable number that you can get, say, in the time zone you're interested in from?
So, yeah, exactly. So M81 as well is an obvious one.
Okay.
Maybe things like NGC 300. At some point, there's like TAC fatigue, right?
Yeah, that's-
So, I don't know, we're not there yet,
Yeah.
but. and,
Okay, so,
yeah, but there are a handful. There are maybe, I don't know, 10-ish halos.
and you think getting some good fraction of this 10 is possible.
Yeah, I think we're on our way to getting, 3 or 4 out of those 10. I know, it sounds a little sad and hopeless, but it's what we can do. Yeah, that's right.
Yeah, I mean, I think just, this is exactly, I think, the right approach to this problem.
All right. Well, let's thank Dave again.